Welcome to Sober Math. I want to show you a surprising result that may have been overlooked, a visualization of equilateral triangles on a square grid. My last videos were pretty intense, so today we take a break with a super quick and easy video. To start off, what do you see? Sure enough, there are three discs with wedges cut out of them, but they are aligned so that the brain tries to see a complete equilateral triangle, even when none is actually there. This is referred to as an illusory contour, and we will circle back to this in a moment. In the original Mathologer video entitled, "What Does This Prove? Some of the Most Gorgeous Visual Shrink Proofs," linked in the description, after the first challenge, the Mathologer treats us to a stunningly intuitive visual proof that even on an infinite square grid of dots, you can't draw an exact equilateral triangle, no matter how big, with all three corners on the dots. But as the Mathologer points out, you can get very close. And a natural question to ask is, precisely how close? At least we know we can draw two corners on the grid and find out how far the third is from a nearest grid point. So we start with a grid of dots and make it infinite, why not? And impose x and y axes with the origin at some grid point, so that all dots have integer coordinates. We lose nothing by confining one corner of a triangle to this origin, since the origin is arbitrary anyway. I mean, come on, grid's periodic and infinite, what more do you need? Now draw a position vector v, which points from the origin to some second grid point. Here we'll call it 4 and 3. We will rotate this point 60 degrees counterclockwise, and the new position vector will point to some third point. And the third point must lie off the grid according to the proof, since these 3 points form an equilateral triangle, well within the precision of the computation. Like my string art video, we rotate a point on the plane using a 2D rotation matrix. The angle is 60 degrees this time. And so here are the exact values of those trig functions. In this example, the old red vector v reaches to point 4, 3. So plug this into the input vector, and we get this value for the tip of the new green rotated vector, which is approximately negative 0.598, 4.964. And again, those aren't both integers as promised by the proof. Otherwise, the third triangle corner given by the green vector tip would lie on the grid. So here's an easy challenge for you. You can use trigonometry to verify this above point without the rotation matrix, and feel free to post your solutions in the comment section. So clearly this doesn't land on a grid point. But how far is it to the nearest grid point? That depends on the location of that point. So how do we find it? We just round both values to the nearest integer. And in this case, the nearest grid point is on its upper left, and the distance of this length is along the gold line. The nearest grid point is at negative 1, 5. And here's the distance formula. And we plug these 2 points into the formula. And here we get that it's about 0.4. It's easy to show that the nearest grid point cannot be greater than 1 by rad 2, or about 0.707. And if it is, there's an error somewhere. So that's it, 1 point down, and a bunch more to go. So let's go to the code. So hey, let's code this up. I'm using Octave, a free version of MATLAB. By trigonometry, a third corner of a triangle has to be within 1 by rad 2, or about 0.707 of its nearest grid point. I put in a minimum value counter to see how close we actually get. Suppose we let Vx and Vy vary independently and plot a contour plot. So here there is 100 points, n equals 100. And here I let Vx and Vy range from 1 to n. We get a confused looking plot that looks like artificial sod. TMI. So what do we do now? So we just varied Vx and Vy independently, but that was too much. So let's pin down one of these values. We can keep Vx fixed, for example. So here I choose Vx equals 100 because why not? And then let Vy range, this time from 1 to 10,000. And would you look at that? Incredible. So what's your impression of this? To me, it looks like Moroccan Alhambra tile art, but draped on a fabric. So if you want to plot this yourself, if you look closely at it, it looks like a regular tiling pattern, but you'll find that this is a stubborn illusion. Upon close inspection, these points don't form a regular tiling pattern. There's almost something rather organic about it. And we have entered into the world of algebraic numbers. So see this center point? Actually, it's two closely spaced points, which upon translation to these neighbors become the spokes of yet another center ring. But exactly how? Where do these apparent shapes come from the level of computation? So see this? What is remarkable is we have a form of self-similarity. So what does that mean? If you stretch it enough along one axis, say like by a factor of 13, you get the forms back again. Something similar happens when you plot the modulus of multiples of an irrational number. This plot reminds me of a pineapple, and especially without the skin. It's made by multiplying an integer k, here I chose k to range from 1 to 200, and multiply k by cap phi. So that's the golden angle, which is about 137.5 degrees, or about 2.39996 radians. And this number is computed modulo 2 pi. That just means we are taking the reduced angle. So all angles bigger than 360 degrees are kept between 0 and 360. And you can see that it closely resembles a tilted square grid. Again, we get a self-similarity by stretching one axis by a fixed ratio. I choose to stretch the horizontal axis by a factor of the golden ratio squared, or about 2.618. So here I stretch it 3 successive times, and the colored lines follow that geometric progression. Observe that each time we get another square grid tilted in the opposite direction. The area of the unit square of this grid has expanded by close to a factor of phi squared. And like our hubs, we see another illusory contour, where the brain tries to see lines piercing the dots. In fact, this square grid is not genuinely square. That's just another stubborn illusion. It's actually very slightly rectangular, and the ratio of the sides of the small rectangle is as close to a square as the ratio of 2 consecutive Fibonacci numbers is to the golden ratio. Speaking as an amateur mathematician, if any of you have a deeper explanation on how this visualization relates to the algebraic numbers and wish to comment on it, I will be sure to give you an acknowledgement in the description of this video. I sure hope you enjoyed this video. If you did, please give it a like and feel free to subscribe, as this will inspire me to post better and more compelling content. And please feel free to leave a comment. It would be great to know what you think and what kinds of topics you are interested in.